Today's lesson, we're going to look at the 3D shape of covalent compounds. So when we say the term molecular geometry, molecules are the name given to the structure of covalent compounds. So we are looking at the geometry or the shape of covalent structures. All we're going to do is start with Lewis structures. So we know how to do Lewis structures from section 2. We're going to take that Lewis structure and be able to determine what the 3D shape will be for that structure. Here's the thing you got to remember. Not only do we have atoms in the structure, but we also have unshared electrons. Those unshared electrons, it's very important to understand this, they're going to take up space just like an actual atom is there. Not all unshared electrons, but very specific ones, do affect the outcome of this structure. So it'll be very important when we look at this that we're drawing Lewis structures correctly, we're drawing single bonds, double bonds correctly, we're drawing all the lone pairs correctly, and we've got a nice, neat, organized structure. So what are we looking at here? What we're looking at is what's called the valence shell electron repulsion theory, VSEPR theory. What's VSEPR theory basically stand for? Well, basically stands for we have the outermost electrons repel each other. What that means is they're going to take up space just like an atom. So we have two examples here of structures. We got water and we've got carbon dioxide. Now, it looks like they're very similar. Okay? I've drawn them left to right, 3 atoms, 1 atom in the middle. I've drawn a straight structure. The problem is they are not the actual do not have the same 3D shape. Why do they not have the same 3D shape? Because oxygen right here has a pair of electrons on the center. Carbon does not. These electrons are acting like another atom is here and another atom is connected there. That will create a totally different three-dimensional shape compared to what carbon dioxide is. When you come into class, I've got the 3D molecules, the little kits that you put together. You'll see that you will use these a lot when you get to section 5. So as you get to those sections, obviously I'm going to be expecting more and more of you to ask for those kits. All right, so how do we do this? It's real simple. After you've got a Lewis structure, you're going to look at that structure and you're going to create what we call an ABE formula. What the letters stand for. A stands for, okay, is there a center atom in the structure? B stands for any other atoms that are connected to the center atom. And then E, and E is always the one people have a tough time, not because it's difficult, they sort of go too fast or confused. E stands for the unshared pairs that are attached to atom A, okay, the center atom. First of all, again, it's pairs of electrons, not individual ones, and the only ones we care about are the ones on the center atom. So what we're going to create is this formula, ABE, with subscripts. Once we have a ABE formula, there are a set of standard shapes that we are going to learn. They're not all of the shapes, but they're a set that we will learn. If I just bounce back real quick to water and carbon dioxide. If we look here at water and carbon dioxide, let me take away the atom here. If you notice, oxygen has a pair of electrons because it's a center atom. Carbon does not. Well, what about the electrons on the oxygen, the outside atoms? We don't care about those. Those are not going to affect the outcome of the shape. It's just the ones on the center. So, what are we going to be looking at? We're going to be looking at several different Lewis structures. So, I've got 4 of them right here that we have drawn recently in section 2. You know, if you've been following along in the notes as well as doing the homework. Water. Okay, so we've got the Lewis structure for water there, HOH. Well, if we take that, apply it to an ABE formula, we're going to get A, B2, E2. So what do we have? We have a center atom, oxygen, attached to 2 other atoms, There's our B2. Attached to the center atom are two pairs of electrons. There's our E2. Carbon dioxide, center atom, A. Two other atoms attached to it, B. There are no electrons on the carbon, so we have no E. You could put E0 if you wanted to, don't need to. And H3, here's ammonia structure. We have a center atom, A. Three other atoms attached to it, B3, a pair of electrons on the center atom. So E1. Again, it stands for a pair. The last one, I have SO3. I have a sulfur in the middle, bonded to three other atoms. There's our B3. And if we notice, sulfur does not have any lone pairs of electrons on its structure. Why did I show these for? Well, the first two, even though I've drawn them very similar, okay, they're linear, there is a difference between their shape. And we're going to determine that based upon water is AB2E2, but carbon dioxide is just AB2. These last two, again, look very similar the way I've drawn them, but they're actually quite different in their real shape. The ammonia one is an AB3E, the other one is an AB3. So what does the E mean? That means these pair of electrons and these pair of electrons are going to act like an atom, which changes the overall shape of the structure. Give you one more here. Here's the formula for methane. Okay, we have a center atom A, four other atoms bonded to it, nothing on the center. We got an AB4. So that's the first thing. You got to be able to draw Lewis structures correctly. And then once you have a Lewis structure, you just look at it and apply an ABE formula to it. And we're not going to have a whole bunch. There's about 8 or 9 that we're going to look at. So let me give you two other oddball examples that don't necessarily have a center. You may run across these, so not a big deal. Let's say we did oxygen, O2. Well, there's its structure. What would we call that structure? Well, we could call it an AA or an A2. There's not really a center. Whereas hydrochloric acid, HCl, we would just call it an AB. Again, there isn't really a true center. Somebody might say, well, what about these lone pairs? Well, again, since we don't have a true center atom, a central atom, we're going to sort of ignore that because it won't affect its shape. So on page 200, there is this chart, and you do need to know this chart. I am not going to be providing this chart or these formulas, so you will have to learn these. The very first one is not actually listed, and we just briefly mentioned it. But if we draw a Lewis structure and we get an AB formula, an AA formula, or an A2 formula, the shape to that molecule is going to be linear. If we have two atoms, if you think about it, and they're bonded together, no matter how you twist them or turn them, they're only going to form a straight line. They cannot form any other type of a shape. So what are we talking about here? We're talking about hydrochloric acid could be that way. You know, here's HCl. So we could have HCl, bonded that way, bonded this way, bonded this way. It's still linear no matter how we spin it. We could also have oxygen, O2. It's a linear molecule. Now, we start looking at some other shapes, and these are the ones then listed in the book. If we draw a Lewis structure and its formula fits the format of an AB2, then that chemical is linear. Perfect example, carbon dioxide. Why is this structure linear? Well, what we'll look at here in a second is the next example. The reason this is linear is because there's no pairs of electrons on this center carbon. If we have a structure that's AB2E, that structure, even though it has a center atom and two other atoms, so that's the same as number 2, but there's a pair of electrons. As soon as there's a pair of electrons, it's bent. So what does that mean? That means this structure right here has a pair of electrons. That pair of electrons takes up space just like there's another atom there. So imagine we're kind of doing a little geometry here. If I've got a nitrogen, and I've got something this way, and something this way, and I got something up here, how are they likely to spread out? Well, we don't expect to see this. The reason we don't expect to see this, here's our little geometry lesson. 90 degrees, 90 degrees, 180. Doesn't want to do that. So what does it do instead? That pair of electrons takes up space. So if we have three things, they're all going to be 120 degrees apart. So that pair of electrons, again, even though there's not really an atom there, it takes up space like an atom. So what happens? All the atoms So what happens there is all the atoms spread out as much as possible. The next example, if we have something that ends up having the format of AB3, then it's trigonal planar or trigonal planar. Well, what kind of a structure can be trigonal or trigonal planar? Well, here'd be an example. We have three different atoms that are bonded to that center carbon atom. Well, they're going to spread out as much as possible. So if we look here, just the example right before, we had a nitrogen with two atoms and a pair of electrons. Here we have a carbon in the center with three atoms. So what do they tend to do? Again, they're not going to form a straight line or any type of a plus sign or a cross sign. What they're going to form is something that is equidistant apart. So all three of those bonds will be exactly 120 degrees apart from each other. So what we have is a triangle of atoms that are in one plane. You're not going to see the plane effect until you actually put some of these models together in class, which you'll need to do. Moving on. Next one. Well, what if we draw a structure that has a format of AB4? Well, it's tetrahedral. We're not going to get something, if we draw a structure like that, oh, it's a cross or a plus sign or a square, an X. No, because remember, it's not flat, it's not three-dimensional. So what we have is, and a perfect example is methane gas, CH4. We have this structure here where we can imagine that this can rotate. We have four atoms around in the center, and it's not flat in one plane. You have all four atoms moving, okay, or positioned in different places equidistant apart. What if you have a chemical that has the format AB3E? Well, if we go back here, AB3 was trigonal or triangular planar. AB3 is also triangular or trigonal, but now it has a pyramid shape to it. Ammonia is a good example. So we have a pair of electrons up here instead of an atom, but there's still something unique to its shape. We have a triangular effect, but what you're going to notice is that it has a pyramid shape to it. I mean, it is not planar. Okay? So pyramid does not mean planar. It's not flat. AB2E2. If we have a chemical structure that has that formula, then it's bent. Water is the good example. So it's not linear. If we come back here to AB2, okay, carbon dioxide, oh, it's linear. Center atom, two other atoms attached to it, okay, straight line. Water, that's not the case because water has two pairs of electrons that take up space. So it's very similar to, if we think about it, kind of like methane here. We imagine this is the oxygen atom. Okay, I make this the oxygen. Okay, there's our O. And I say instead, oh, I'm going to make this, instead of a hydrogen atom, a pair of electrons. Instead of this hydrogen atom, a pair of electrons, what's left to the shape? That's water's molecule. Okay? So everything is still positioned in the same place. We give it a different name to its shape because if there's more atoms or less atoms, it changes the name, but we still see some consistency in what that shape is. Okay? Last two, and these two kind of break some rules. So as I talk about these are not ones that I'm going to expect you to be able to draw or predict. If you ever see a structure that has AB5, you think, wait a second, B5, that means 10 electrons. Can't happen. Octet rule. You're right from what we've learned so far, but there are ways the octet rule is broken. You don't have to worry about it yet. But if there is a structure that has an octet or greater than an octet in which it bonds 5 things, we're going to call it a triangular bipyramid. So we have two triangles, a top triangle and a bottom triangle. Phosphorus is a great as an element that does that. So if we can see this structure here, we've got a triangle of 3 chlorines attached to the phosphorus with a chlorine above and below. So what we really have is there's our bottom pyramid and there's our top pyramid. Bipyramid, 2 pyramids. The other one, if you have something that's AB6, which again you only recognize if it's given to you, it's called octahedral. Now, I might be wondering, no, wait a second, octahedral, that means 8, but I only see 6 things or 7. Well, you're right, but if you look in the book on that page, you're actually going to notice that there are 8 faces to that structure. And as you look at that structure, you're going to see that's where they get the prefix octa from, because there are actually 8 faces to what that structure has. Another way to look at this is you have 4 fluorines basically in an X formation in one plane, and then you have a fluorine above it and below it. So one in the middle, one above, one below, and then 4 in the middle. And you can see that picture in the book. Make sure when you're doing these that you need to be able to look at these different structures, be able to put them together with the different molecular model kits that I have. Otherwise, you won't be able to put them in your hand and figure those things out. So when you get to this section, again, I'm expecting you to be asking questions. Hey, where's those model kits at? Can I have one to start putting some of these together?